Hi everyone, so today we are going to be going over question 1 of homework 1 of cell engineering. So a lot of you have had MATLAB questions, so hopefully this will help you as a quick tutorial for MATLAB. So looking at the question statement real quick, basically what we've been given is a set of data. So we have an input, which is this ligand concentration that has been changed, and then output is the binding signal for this wild-type protein as well as this mutant protein. So what we've been asked to do is, using MATLAB, use the invent-fit function to calculate KD and a signal coefficient. So KD and a signal coefficient are both part of the equation that you are asked to fit this data to. And if you're not sure what I'm talking about, please go to the end of Dr. Green's lecture 1, where he gives you some homework hints, and take a look at that. But basically, after that, we are asked to do some plotting. So we're asked to plot an overlay of the fit and the experimental data. So in the same plot, you're going to have the experimental data and then the calculated values from the equation that fits the experimental data. And then the second plot, you're going to have the residuals, which is the difference between your data and your fit. And so I would recommend actually making 4 plots total. So for each of the proteins, you're going to have one plot doing the fit and experimental data, and then one plot having the residuals. So without further ado, let's get started. So what I'm going to do is actually run through the process of using invent-fit to find constants and to do the plotting by using this example problem. So here you see that I have x values and y values, just like you've been given in the problem. And here's the equation that I'm trying to fit to. You can see it's a non-linear equation because it's a difference between two exponents. And I have written in red these a and b values, so these are going to be constants that you're going to find at the end. So that's similar to what you're trying to do in terms of finding KD and alpha for the homework. So let's open up MATLAB, and when you open up MATLAB, you're going to have something that looks like this. For those of you who have never seen it before, what you're going to have is a script window and a command window, and yours might not look exactly like this. It might be the script windows on top and the command windows just on the bottom. I just have it laid out like this. But basically, what I'm going to do first is I'm actually going to define a function. So this is the way that Dr. Green has it set up in your template. And the beginning part is a little funky because even though you type in the word function, you're not actually doing a function per se. But this part is just so that you can input data and call MATLAB to do things. So it's slightly strange, which is very free. So you can basically name it anything, and for my purposes, I'm going to name it data entry. I think Dr. Green has it as my flag in his code. But I'm going to call it homework 1 example problem. And then make sure you hit parentheses so it knows that it's a function. And so in your actual problem, when you're doing the homework, please put homework 1 cell engineering and then your full name so we know who you are. Okay, and the practice to do is always say clear all and close all. So this is to clear and close anything that has come before. Obviously, we've just started MATLAB, so there's nothing to close, but later on when you've been troubleshooting, you have stuff, and this will be easier. And then this part is the strangest, because trust me, just call it data entry equals 0. So I'm not actually telling it to do anything, so there's nothing that the data entry function is doing, but this is just to get things started. Okay, so like it's called data entry, so let's enter some data. So I'm going to enter my X data. Okay, so I'm going to enter my X data, and over here you see that it's laid out in columns, and so we're going to do something kind of similar, where in MATLAB they like to have everything entered kind of like matrices or arrays. So I have the bracket sign, and then I'm just going to enter everything followed by a comma. Okay, and then same goes with my Y values, so I'm going to enter all my Y values in brackets as well. Make sure that when you're entering, though, that you copy it down correctly so you have the same number of values in your X as well as in your Y, because if the matrices don't match, then your code is not going to work. Okay, so that should be that. And then for now, I am just going to end this function, but I'll show you guys that we're going to actually do more with this, but it just makes more sense logically to do it in this order. So now I'm going to define a second function, and this time it'll actually be a function. So what I'm going to try to do here is to type in the function that I'm trying to fit so that MATLAB knows that these data go with that function. So I'll just name it example function and then give it a name. So I'll call it function to fit. And make sure that when you name functions, you don't actually have spaces in between, because then that's going to be a weird syntax error that's going to come up. And whereas up here I had empty parentheses, down here I'm actually going to give it some variables. So if you look at this function here, it's actually a function of x and a function of these constants here. So that's what I'm trying to say here, is this function to fit is a function of x and constants. And then later on I'll define the constants a and b. So then I'll actually tell MATLAB what my function is. So example function equals, so type this guy in, exponential. Okay, so now instead of typing in a and b, I'm going to refer back to this guy here and say that a is C1 and b is C2. And this next part is important, so pay attention here. So instead of just typing exponential C1 times x, what I have to do actually is C1 dot, C1 comma, period times x. What this means is, so the period modifies the multiplication sign. Because I'm multiplying a matrix, I have to let MATLAB know that I'm multiplying this matrix, this value by a matrix, and not just like a value by another value. And so that's what the period is for. And then same goes with the next part. So make sure you have that period in front of the multiplication sign. And the same thing goes with division. If you're going to be dividing by a matrix, you also want to say period divide instead of just regular divide. Okay, so now I have the function that I'm trying to fit, input, and I'm going to actually define what these guys are, so what C1 and C2 are, so that later when I run my code, it'll tell me my A value is this and my B value is this. So to do that, I'm just going to say A equals C1 and B equals C2. So that when I run my code, it'll say A equals this and B equals this, so it's easier to find. Okay, and now I'm done, so I'm just going to say end. Okay, so let's go back up here. Now that I have my function, let's go back up here to actually do the fitting. So before you actually fit anything, you need to tell MATLAB where to start, because the inline fit function is actually kind of guessing iteratively, if you will. So you have to give it an initial starting point, and then it'll input those values in, take a better guess, input other values, take another guess until it gets as close as it can. So I'm just going to give it initial guesses for my A and B values, constants. So I'll put it in an array because MATLAB likes this. So I'm going to guess 0.01 for A and 0.01 for B. Okay. And then I'm going to do my inline fit function here. And for starters, I'm just going to call it coefficients because what I'm trying to find here are just the coefficients A and B here. So I'll say coefficients equal inline fit. And if I wait a while, it'll actually show me what I should be putting in for this function. So it needs me to put in x, y values, so I'll just put x and y. It wants me to put in this model function, which is this function that I put in down here. It's what I'm trying to fit. So I'm going to go at function to fit. And this at symbol just calls the function to fit that I've defined down here. And then I'm going to say this beta 0 is my initial guesses because it needs to have a starting point. So I'm giving it the initial guess. So that's everything. Close out my parentheses. So again, inline fit, and then you need to put in your x and y, what you're trying to fit. Call the function that you're trying to fit. So function to fit using this at symbol. And then the last component is the initial guesses that you give it. Okay, so now the function is done, and I'm actually going to run this real quick so you guys can see what this little bit of code does. So if I hit run, it won't actually let me run unless I save it. So you have to save it first and make sure, MATLAB does this already automatically, where you see how this guy matches this title right here. So make sure you don't change this down here because the path needs to match. If you named it something different down here, then it won't be able to find the right code or something, and then it won't run. So just hit save, and it's strange. Hold on, let me just try that again. Okay, so whatever. Okay, but you do see that this code ran. So basically, if I scroll back up, you'll see all the different iterations. So starting at the values that I gave it, which is 0.01 and 0.01, it did a bunch of calculations, and eventually it got to the point where it tells me that it thinks that A equals 0.09 and B equals 0.022. So I found my constants A and B right now. So that's good. So that's part of the thing that you guys are asked to do, and the other part now is to just plot everything, which is a lot simpler than the actual fitting. So to plot something, you have to call a figure. And then, so this part is slightly different than what you guys are going to be asked to do on the homework. But on the homework, you're going to be asked to plot using semi-log x. And what this means is that the y-axis is still going to be linear, but the x-axis is going to be logarithmic. And that makes sense because if you look back at the data, the y values are actually not all that different, but the x value goes through several orders of magnitude, so that would make sense. But if you look at the set of data that I have here, the x values actually don't go up by much, but the y values span several orders of magnitude. So I'm going to switch things up on you guys. I'm going to actually use semi-log y here. So it's the same concept as semi-log x, except in this case, x is linear, y is logarithmic. In your homework, you're going to use semi-log x, but same concept here. So I'm going to plot x and y. So this plot is going to actually be for the experimental data. And nifty little trick here for people who've never seen MATLAB. So if you want to annotate your code, like just make a little note that's not going to be run as a code. It's just a note for yourself or for the TAs. What you would do is hit the percentage sign, and then you can put whatever notes that you want. So here I'm just going to make a note to myself that this is going to this will plot experimental data. Okay, so it's in green because I've done the little percentage sign. This won't actually run in the code, it's just notes for myself. So semilog x, semilog y, xy that I have in my code. And then good plotting practices, you want your x axis to be labeled, so x label, and then this part, let's make sure that you guys catch this. The first thing is what you're actually going to label it as. So I want it to be labeled as x values. Except I can't just type it in like this because it's going to think it's going to need to do something with it. So if I want to input a string, aka just have the actual text that I inputted be there, I have to put in these guys. So they're not quotation marks, but it's the single ones. The apostrophes, sorry. So I have to put the apostrophes surrounding it so it knows, and you see how it changes color. So it's like, oh, this is actually a string, not a code. Okay, and then the next thing that I'm going to do is specify font size. And so I'll say font size 14. Okay, and end it. Same thing with the y-axis. So just going to do y label, y value, same thing. And then finally, you want to give the chart a title. So I'll say title. And then again, remember your apostrophes. I'll just name it example graph. Font size, let's say 16. Okay. So I have all the labels, and the next thing I need to do is actually specify my axes, right? So you want to always make sure that you're plotting in like a reasonable value range of values instead of something crazy. So I'm going to say, you guys can play around with this a little bit when you're doing your actual plots, but the way that this lays out is, so axis, and then I'm going to input my axis limits as an array. So then the first two values is going to be the lowest x value and the highest x value. So I'm going to say 0.5 to 95 because that's what my data range is in. And then the next two values is the same thing, the range bound for the y value. So in that case, I'm going to say 0.01 and 5,000. Okay, so then finish up my array in parentheses. Okay, so let's run this again now so that you guys can see what we've done so far. So I hit, actually let me bring back my command window. Okay, so I'm going to hit run. Runs through everything, and it's going a little slow. Okay. So runs through everything and it plots figure 1 for me. So you see we have y values, x values. I did semi-log y. So semi-log y, logarithmic y-axis, and then linear x-axis. And this is my values that I have inputted right here. So everything works out great. So out of that, so on the same plot, remember I told you guys that we should also plot the fitted values. So Dr. Green mentioned this in class, but how to do that, how to put two sets of values on the same graph, we're going to say, hold on. So basically this is like, okay, just because you plotted the first set, we still need the second set. So just hold it, we're going to put in the second set of data. So this part is slightly trickier than the first part because you actually have to calculate the values that you're going to be plotting. So I'm going to define this the set of x values, and I'm going to call it n. So if you have an equation that you fit it to, you're going to want to input something for the x. So this is just trying to say that I'm trying to define a range of m values that I'm calling m to put into the equation so that something else can get spit out on the other side. So I'm going to say n equals, and this part is also a little different from your homework, so pay attention here. So right here, I'm going to say, okay, so now we are here. And before we go any further, sorry for the discontinuation, my laptop ran out of batteries. So this is the second part where we're going to plot the actual fitted values into the same figure as the experimental values. And again, just to be consistent with last time, I'm going to hit the percent sign and just make a note for myself and tell myself that I'm actually going to plot the fitted values here. Okay, so again, like I said before, M is going to be our input, and this is going to be a little different than your homework. So I'm going to say lin space. So what this function does is it actually just gives you a set of values. It generates a set of values, and the lin space is that I'm trying to tell it that the values that it generates should be spaced out linearly. So you see that it gives me two options. So x1, basically I need to put in my range of values that I want. So my smallest value that I want here is going to be 0.1. And then my largest value that I want it to generate, the upper bound, is going to be 100. And I want n 1,000 values. So give me 1,000 values linearly spaced between 0.1 and 100. So that's what it does. And for your homework, because remember your x values are exponential, that's why you have to use semi-log x instead of semi-log y, you're actually going to be doing log space. So log space is almost the same thing as lin space, except it's slightly different, and I'll give you a hint. The first two inputs are going to be different than what I'm doing here. I'm not going to go through that with you now, but just go to Google, look up log space MATLAB, and you'll figure it out. You're smart people. Okay, so now I have my values that I'm going to input into my fitted function. Time to actually fit the function. So I'm going to define the data that it spits out as fitted data, and then just put it in my function. So exponential of, going to call it coefficients 1, coefficients 1 times m minus exponential coefficients 2 times m. So same deal, coefficients refers back to this guy. So I got my coefficients a and b from the inlet fit function, remember? So now I'm just going to call it, so coefficient 1 is a, and then coefficient 2 is b. Okay. And then I am going to, so now I'm done with that part, and it knows what it's supposed to calculate. Now I just need to do what I did here again. So instead of semi-log y, x, and y, because I already gave it the values, I have to refer back to it where I've calculated. So I'm going to do semi-log y, and this time I'm going to call it. So my x values are going to be m, and my y values are going to be my fitted data. Okay. And then, because now I have two sets of values, good plotting practice dictates that I need to put it in legends. I know which one's which. So this is pretty simple. The first one, the string, is going to be the data that I input. And then the second string is going to be the fitted data that I have input. So they're both strings, and this just goes first because this guy went first. Okay, and so now we're done, and I had it to hold on, and now I just tell it to hold off. So it's like, you can go now, I'm done. Okay, so now we have everything, and let's hit run. And I have the graph. Okay, so It might not look like a lot of things are different, but if you recall from last time, what we had was only the blue line, which was the data, and now we have this red line, which is the fitted data. So I was able to plot my original data and my fitted data all in the same graph. So great, that's part of the problem already done. Okay, so now all we're doing is one last part. So one last part, we are plotting the residuals. And because I want it in a separate figure, I'm going to call another figure. And this time I'm still doing semi-log y. And I'm going to say the x value is just x and the y value is the residuals. And this is where you go, hang about a minute, where did you do residuals anywhere? And this is where we go back to the coefficients. So in the homework hints that Dr. Green had, he had actually said that the second option for inland fit, the second output is going to be residual. So we just need to format this slightly differently and then it'll all work out. So instead of just calling it coefficients, which I did at the beginning to simplify everything, now I'm going to have this as an array. And I'm still going to call it coefficients. That's going to be my first thing that I'm going to be spitting out, but I'm also going to have it spit out the residual as my second component. So now I've defined my residual, which is just something that inland fit automatically spits out already, but I just needed to define it, and now I've defined it, and I can plot it. Okay, so same deal, XY label and titles and stuff. I can just copy and paste it here. So just make sure X label is still X values, and I'll change Y label to say residual. Title, I will change to residuals graph. And you might want to play around with the axes a little bit as well when you're doing your homework, but I played around with this already, and I know that in order to see it properly, this is what I'm going to do. Okay, so this is my range. And so I should be done. So cross your fingers and hit run again. Okay, so it found A and B. And now we have two figures. So where we had figure 1 was data and fitted data, now we have this. So this isn't super exciting. Yours for the actual homework will look better. But yeah, so I have the actual value, so that's great. And yeah, so that's actually all there is to it. If you look back at the problem assignment, problem statement, we have found our two constants. We've plotted an overlay of fit and experimental data. We've plotted the residuals. So what you would do in your actual homework is you would just repeat the process one more time. So say that first set of graphs was for ligand versus wild type. Just do the same thing with mutant. Couple different ways to put that in. You could just put it in completely different as a separate set of functions, that's fine, or you could just go ahead and put the second set of data up here and then just repeat down here, but you should be able to figure it out from here. So hopefully this helped you guys. I'm sorry if it was a little long. So questions, comments, concerns, email us with TAs. Yep, see you in class.